Okay, folks, so we're going to look at some applications of integration, and really we've done a bunch of this work before, but in this section we sort of summarize a few of these pieces as well as just simply revisiting some others. So the first thing I want to look at is this area function that we've been studying for a little while now. So g of x is our area function. Something very important to keep in mind, I think, is that the independent variable here is specified to be x. Where does x show up in the expression of the function? It shows up as the upper limit of integration. I think that's really important to keep in mind as you're working through these. Okay. So I actually probably didn't give you enough room to really write out a lot of these problems. But I think we can still go ahead and evaluate this slightly. If I ask you to evaluate, let's skip g of 0 for just a moment. Let's compute g of 1 real quick. By definition, what does that mean? Well, it means to evaluate the integral from 0 to what? Well, to whatever x is. In this case, x is being played by 1. So we've got the integral from 0 to 1 of f of t dt. And now we just know how to interpret this statement as the definite integral. The definite integral from 0 to 1, what does that measure? That measures the net area between the curve and the x-axis. And so in this case, the definite integral from 0 to 1 is simply the area of this region here. Now, if I gave you what f of t was in a functional format, you could go ahead and compute that using the fundamental theorem of calculus. Additionally, there's nothing to stop you from doing a limit of Riemann sums, but don't forget, this is always asking us for an area, and if you can compute area by another means, you're welcome to do so. So specifically, this entire shape is comprised of either horizontal or slope lines, and so we could go ahead and simply add up the regions using our knowledge of the areas of rectangles and the areas of triangles. Here we have an area, or here we have a shaded region which is rectangular, and it's got a height of 2 and a width of 1, and so the area of that region is 2. Similarly, if I asked you to compute g of 2, that would be the integral from 0 to 2 of f of t dt. And in this case, I'm asking you to include an additional, this green area in addition to that blue area. And if we add those together, well, I have just added another rectangle, in this case of base 1 and height 2. And I've also added a triangle, and in this case that triangle has a base of 1 and a height of 2. And so the area of this first piece here is 2. The area of this triangle is 1. Why is that? Because the area of a triangle is 1/2 the base times the height. And of course we already said that the area of this region here was 2, so we've got 2 plus 2 plus 1. So the area underneath the curve between 0 and 2 is 5, so g of 2 is 5. Okay, let's go back and pick up g of 0. G of 0 is 0, and I'm going to let you compute the remainder of these. So you go ahead and find g of 3, find g of 4, find g of 5, g of 6, and g of 7. I guess you would want to leave yourself enough room to compute these. Okay. Then I want you to go ahead and answer these questions. On which intervals is g of x increasing? So I will go ahead and give you these answers, but I want you to check them based upon your answers to part A here. So g we will find out is increasing on the interval from 0 to 3, and I want you to see as to why that is so. And when is f of x positive? Well, f of x is positive also on the interval from 0 to 3. Where is g decreasing? Well, g is decreasing, you'll find, on the interval from 3 to 7, and f is, of course, negative on the interval from 3 to 7. Okay. I want you to think about these two questions. Where does g of x have a maximum value, and where is f 0? And from there you can go ahead and then sketch a general graph of the function g. Notice we've already found a few ordered pairs on this graph. For instance, we know that if we plug the number 1 into g of x, it outputs a 2 because we inputted a 1 for our upper limit of integration, and we found the area underneath the curve of f of x was 2. Likewise, when we inputted a 2, it outputted a 5. So I'd like you to go ahead and plot that value as well. And when we plugged in 0, it spat out 0. And go ahead and plug in the remaining values and see what you can see about the graph of this curve. We'll talk more about this in class, But here is the big result here. Notice that wherever G was increasing, F was positive. Wherever G was decreasing, F was negative. That relationship should look very familiar to something we've seen before. And that relationship is the connection between a function and its derivative. Therefore, the relationship between f and g is g prime of x is f of x. That is, the function that describes how g changes is just the underlying shape of this curve, in this case f. Okay? Then I'm going to let you go ahead and try number 2 on your own, and we will go through this one in class next time as well. So now is a good time to stop the video and continue working through the remainder of the problems we didn't get to on this first page.